Good morning, everybody. Welcome to physics. Today we got just a little review of some of the things we've talked about here, maybe a better explanation for you. A little help for the homework assignment. First thing we want to talk about here is the average velocity. Okay, and the formula for that is average velocity is displacement per time. Now, x without a subscript is final, and whenever we don't have a subscript, it'll be a final position. Or velocity, depending on whatever variable we're using. But in this case, it's position minus x sub naught, and that means at 0 time or at naught time. So really final minus initial divided by the time that it takes to get from that x sub naught position to the final position. And that's one of our average velocity formulas. Okay, so if you look at our at an example, let's just say that we have somebody moving, 5 or 15 meters to the east, and let's say that it takes them 3 seconds. So if we kind of just fill that in, we'll say that we have a 15-meter position change in 3 seconds, and we have 5 meters per second to the east. You got to remember to put that east in there or some kind of direction because this is a vector quantity. So if we look at the graph of this situation, and we'd have a displacement or a position time graph, and we could say that we start at 0 and we move 15 meters in 5 seconds. We would have our other point here, and we could say that this is the graphical way to show this problem. And remember we talked yesterday about this line and the importance of it, and every line has a slope. And slope is, rise over run or rise over x's. And in this case, our y label is meters, our x label is seconds. So the slope of this line then is indicating velocity. Okay, so that's kind of average velocity for you. Now I will give you one more velocity formula. So average velocity can also be v plus v initial, or v sub naught, divided by 2 if an acceleration is constant. So that's kind of a teaser for the beginning of next week. Acceleration is, you don't really need this today for today's formula, but acceleration is the rate of change in velocity per time. So we'll talk about that next week, but that is another average velocity formula. Like I said, this here only works then if we have a constant acceleration, but in this case, we have a constant velocity because we have a constant slope, so it doesn't have to do with that graph. Okay, so let's just take another look at final velocity then. So if we have a graph, let's say that is like this, okay, and we have a velocity time graph in meters per second over seconds, and we do have a constant acceleration. Let's say that we hit 10 meters per second, and it takes, let's say, 10 seconds to do that. Then the graph would bring us over to this point here. Now this is a velocity time graph, so this is a little different situation. But under constant acceleration, which is what we do most of our math with, we would have constant slope. And just to make sure that we're correct on that, we'll look at the y's over the x's for this velocity time graph, and we can see that we have meters per second over seconds for our label, and meters per second is our label for acceleration. So the slope of this line then is acceleration. Now, if we're talking about v sub naught, or initial velocity in this case, it would be 0 because we're starting down here. But our final velocity, then, in this case up here, would be 10 meters per second. Okay, so that's our final velocity. And these velocities, and when we start looking at these variables, unless it says average, these velocities are always instantaneous. So for just the first instant, we have that initial velocity of 0, and the last instant, we have that final velocity of 10 meters per second. And we'll be working more with acceleration next week, but if we want to go to, from that into our kind of definition of instantaneous velocity, it's kind of easy to see on that last graph, because we had this really constant slope, and anywhere on that slope it would be pretty easy to figure out what the velocity of that is, because we say instantaneous velocity is, or velocity would be, instantaneous at any point in time. So, on this graph it's kind of easy to see what the instantaneous velocity is, because at any point in time you could say, well, that's what our velocity is. Okay, but if we look at displacement time graph, okay, so let's look at our displacement time graph. So we have, x over t, or meters per second, okay. Then if we look at this line, this is a constant change, right? So a constant slope. And we already said that the slope of a displacement time graph is meters per second, okay, which indicates velocity. Now the slope of this line here is the velocity. So in this case, if I said, well, at this instant, what's my instantaneous velocity? Well, it would really be the slope of the line at that point. Well, that's pretty easy to tell here because it's right on the line, right? Or here, it would be the slope of the line at that point. Well, in fact, the slope of the line at any of these points here is going to be constant. Okay, so this is a constant acceleration, instantaneous velocity, or this is a constant velocity, excuse me. So instantaneous velocity would be equal to velocity at any point, would be equal to the average velocity, because this is my final displacement, my initial displacement. So displacement per time at any point in this line is going to be giving you an instantaneous velocity. So if we looked at a velocity time graph of this situation, it would be just a constant straight line with no slope. But let's look at something like this, okay? Because you can tell now that this is not going to be an instantaneous velocity, because we see here is a slope, and if this is a slope of a distance time graph, our rise over run is going to be meters per second. The slope of this line here is different than the slope of this line is different than the slope of this line. So here we have accelerations. We're changing our velocity. So how do you find instantaneous velocity on this graph? Well, if you would ask, at 1 second, what is my instantaneous velocity? Well, what you would do is find the slope of the line that goes through that point, and you would find your instantaneous velocity there. So in this case, the slope of the line would be 5 over 2 meters per second. That would be my instantaneous velocity for this first part of the line. Well, how about this piece right here? The slope of the line between 2 and 3, it looks like that guy just stood still there for a second. So there's no slope. There's 0 meters per second for this whole portion of time. And at any instant along this line, it's going to have an instantaneous velocity of 0 meters per second. Now here you can see the slope is going to be greater, and that slope looks like it's going to be 20 over, well, that's not 20, is it? That's 15, right? Because that's going to be 15, right? Because we start at 5 and we end at 20. So 20 minus 5 is going to be 15, meters for every we go. That takes 1 second, 2 seconds. Actually, this should be lined up probably right here. It looks like so. That takes 1 second. So the slope of the line at that point is 15 meters per second. So what that means is any point along this line here then is going to have an instantaneous velocity of 15 meters per second. Okay, but what would we say then if we had an average velocity for this whole entire graph? Well, average velocity could be, determined in a couple different ways. Average velocity could be, taking all of these individual velocities and weight their time accordingly and come up with, kind of like a weighted average that you did in chemistry, and you could find out an average velocity. But what's actually a little bit easier here for us is we can just take our final position and our initial position, and between those we will draw a line. And if we find the slope of the line at that, anywhere along that line, that slope of the line will be an average velocity. And so it kind of follows our formula. Average velocity then is this final position minus initial position divided by time. So in this case, our final position is 25 minus 0 over, what do we have? 6 seconds, over 6 seconds. So our average velocity is 25/6. I would suggest in the homework that you put that into decimal form. I don't have my calculator on me right now, but that is the way that we would figure out the average velocity for the entire situation. Now there's one other thing I want to show you. If we had a displacement time graph that would look like this, how do you find an average velocity at any instant? Well, if I was going to ask for this right here, what you need to do is find the slope of the line that point goes through. Well, the only way you can do that is draw what you call a tangent line. Okay, so a tangent is a line that hits the curve in just one point. And then you would find, two positions along that tangent line, and then you do your difference of y's over your difference of x's, and you would get a slope. And you should know then by now that the slope is equal to meters per second. And that would be the way to find the instantaneous velocity when we have this curvy type graph. Okay, well hopefully that helps you with your homework. The rest of it is just going to be kind of plugging and chugging numbers. Hopefully you have a good weekend. Thanks. Have a good day.